Okay, so I'm deliberately, my umming and ahhing was, do I give you a specific rational function and talk about it, or shall I just talk about general rational functions? And so I'm going to go for the harder path, which is just to talk about rational functions in general. So the challenge that I've got up there is show that rational functions don't have turning points. Now, when mathematicians say show that, they don't mean ta-da, like that, right? So just for the video's sake, I'll just say that I've got a drawing of a base rational function here off to the right, off to the left, off the screen. And that's the basic picture of it. And you could say from that picture, it feels like, it looks like there's no turning points, right? So remember, turning point is a change from increasing to decreasing or vice versa. So there's no turning point. I don't think I think you could quite safely argue from the picture that there is no change in concavity either. So that's another second result there, I think. But that's just from the picture. So when a mathematician is asked to show something, this is what they need to do. They need to use some sort of algebraic process which demonstrates that it is not true, particularly that it demonstrates that it's not true for all of a set of stuff. Now, I could have given you a specific function. I haven't. I've just said, show that rational functions don't have turning points. I'm going to give you 1 minute, either by yourself or with someone else, to think about the approach. What I'm going to do is, this is just going to be like a slow reveal. Give you 1 minute to think about approach. You can return back to the class and say, this is how I started to think about it. Feed that back to the whole class. If no one has a clue, then I'll just give a hint out and then I'll let you keep going. Okay? So just one hint at a time. So how are you going to approach this question? I'm going to pause the video while people do that. Okay, peeps.
It's just exponential. Sure, why not? Oh. Because it's always going to be one. So kind of. I think it's always going to be one.
Here we go. I've been around to the different groups and everyone's already made it start without me having to give too many hints. We had some really interesting discussion, and I like that I didn't have to give you any hints, even if you didn't quite get there. Like, for example, over there was a very interesting discussion about whether if you could argue that the points are 1-to-1. In other words, that it never, like for an input like x equals 2, there was only one output. That would mean that there's no turning points, because you would have to do this, wouldn't it, to have the same output again, there and there, like that. So that's not bad thinking. I gave a counter example to that, but just one. Another thought from over there, if you don't mind me saying, was that it should have a power for it to be turning, because we know that polynomial functions are either like that or like that or like that, whatever. Not bad thinking, but there are definitely functions out there like the sine function which don't have the power but definitely have turning points. And then the challenge was, well, what properties do we have which allow us to consider turning points? And I think we got there in the end. That group certainly did. That group did. And I think you guys were talking about it as well from memory, and that is derivatives, calculus. And specifically, Will, what's the property of calculus that we can use for turning points? Great. So we know a turning point, whether it's a maximum or a minimum, the tangent to that is a flat line, i.e. gradient is equal to 0. So remember that a derivative is a gradient. It's a gradient function, to be more precise. So if we can prove that f dash of x cannot equal 0, then we've proven that it does not equal, that it has no turning points. Does that sound legit? Okay, the next thing, though, is I told you I gave you the harder challenge, and the harder challenge was, I said, show that rational functions don't have a turning point. not here is an example of a rational function, show that it doesn't have turning points. You could do that. You could say, well, let's say y equals 2x plus 1 over 3x minus 2, and you could then find the derivative of that, but that only proves it for that particular function, doesn't it? Doesn't prove it for all rational functions. So how can we prove it for all rational functions, do you think? Yeah, thanks, Lily. We start with the general form of the function. Now, let's, for the sake of it, assume that b isn't equal to 0. Because if b was equal to 0, then the whole bottom it wouldn't be a rational function anyway, really, would it? I mean, a could be 0, because then you'd have a reciprocal function. But let's assume that b is not equal to 0. A, b, and d can be anything they want to. Now, I'll pause the video in a second, so I want you to have a go at doing this. We've now got a function f of x. Now, one of the mistakes I saw in the exam is that you treat, not everybody, but a lot of you, so forgive me if you're not one of these people, you tended to treat any variable as differentiable. But in fact, with ax plus b over cx plus d, with a function with generic symbols like a, b, c, and d, sorry about that, for all intents and purposes, a, b, c, and d represent static values, right? We don't know what those values are. I'm almost inclined to call them pronumerals, like they stand in for numbers, which is an old-fashioned word for variables, like you might have come across in in grade 7 or something like that. They stand in for numbers, but they stand in for specific numbers. So number one, when you differentiate, you don't treat them the same as x. You treat them like as if they were 1, 2, 3, and 4. You treat them like constant numbers. They're constants. So that's the first point I wanted to make. And people made that mistake on the exam. They had to differentiate something with k in it. And they just went, well, k squared is 2k when you differentiate it. Nah. The other thing that gives it away is this. It's a function of what? I've got my pointer on. It's a function of x. It's not a function of a. It's not a function of b. So when you differentiate, and this is why language is powerful, what we actually say is we are differentiating, I'm going to shout, with respect to x. That's really important. WRT, x, with respect to x. So when you differentiate, the other constants in this instance basically the other pronumerals, the other variables, the other letters are treated like constants. They're not being differentiated, only x is. So that means, for example, a b will disappear when you differentiate it. I'm gonna pause the video and I'm gonna ask you to now differentiate ax plus b over cx plus d. What makes it more challenging is that I've given you a's, b's, c's, and d's instead of actual numbers, but you've got this. You can do it. Before I start, though, I just want to check. Have you moved further ahead, have you? Okay, I'll come and talk to you guys in a second. Before the rest of you start, I just want to make it really clear. Not clear. I just want to do a quick think check. Remember, with differentiation, when you've got something like this, ax plus b over cx plus d, you can't just differentiate the top and differentiate the bottom. That's not how it works. There is a rule that we use for this kind of differentiation. Starts with q and ends in quotient. What is it? Quotient. It's the quotient rule. So if you don't use the quotient rule, you won't get it right. It's in your information sheet. It's in your textbook. I could write it up on the board. I've shown you a process that I believe in to work out use the quotient rule, but do it and see what you get. Simplify it as best as you can. Okay, so this is just for the recording. Here we go. We've got f of x equals ax plus b over cx plus d. We're going to say c can't be equal to 0 because otherwise it would be trivial. And to work out that it's a turning point, most people around the room have determined that finding that the derivative equal to 0 would be the derivative can't be equal to 0 would be enough. So we're going to find the derivative. So f dash of x and see where it takes us. So f dash of x is equal to, we have to figure it out. I'll put the thinking off to the side here in slide 4. The quotient rule is that if f is equal to u over v, so f is a function and u and v are two mini functions, then f dash is u dash v minus v dash u all over v squared. Okay, so my way of doing it is to simply write down u and write down the top, in which case is ax plus b, and therefore u dash is equal to, so with this, we're just going to use the power rule on ax plus b. X is a power of 1, so I subtract 1 from the power, it becomes x to the power of 0, so it disappears. And so I'm left with a, and b disappears because it is treated as a constant, so it's just a. Similarly, with v, I've got cx plus d, and so v dash is equal to just c. Then I tend to put square brackets here and here to say these two are linked and the outside is linked. And we're going to go inside minus outside. I think it's a visual way of keeping track of your thinking. Remember, sometimes it doesn't matter how smart you are. If you're juggling lots of mathematical balls in the air, it's easy to drop them. So having little techniques like these square brackets keeps track of your thinking. Okay, that's why we do it, so you can keep track of your thinking. So f dash of x, I can now write down as the inside, which is a outside of cx plus, a outside of cx plus d minus the inside, which is c outside of ax plus b, all over cx plus d all squared. Now, at the moment, I cannot see any reason to expand the bottom because, I'm just trying to prove that it's not going to be equal to 0. So I've got a denominator which is something, cx plus d. I know that's not equal to 0. I also know it's positive because I'm squaring it, right? So it's always going to be positive. I'm just interested in the top. I will expand that, and I'll get acx plus ad minus cax, but I'm going to put that in alphabetical order, acx plus bc. So I just put, there's no reason why other than it makes it easier to see like terms, putting variables in alphabetical order. But you can see now, I hope, that we've got two terms, acx here minus acx, that are going to eliminate from each other. So we're left with, I've stuffed that up, haven't I, slightly? Wouldn't be a Richard lesson if I hadn't stuffed something up somewhere. Let's be honest. Go for it, Para. What do you want to say? Thank you. You know what? For the first time, I actually felt he really meant it when he said it that time. It was just dripping with disdain. You're an idiot. No, fair call though. So we're left with AD minus BC over CX plus D all squared. So I'm going to go to the next screen in a second. But is that okay with everyone? Yep. Okay. Cool. So I'll just rewrite that again so it's on the screen. So we've got f dash of x equals, I want the whole thing. What was it? AD minus BC. Thank you. AD minus BC all over. Oh man, it's the bracket followed by a C that gets me. CX plus D all squared. So we can see, is that enough to prove that it's equal to, that it can't be equal to 0? Not quite, is it? We can see that it's going to be, the bottom can never be equal to 0, so that's fine, because if it was, it would be an error anyway. But what we're left with, unfortunately, is that the top could be equal to 0 if we chose our values of A, D, B, and C. Okay? Here we go. Now, guys, the two dents down the back here have progressed past this, and we did it by plugging in numbers, didn't we? Shall we see if we can do it just using algebra, which would be more robust? See how we go. Down the rabbit hole. We ready to go down the rabbit hole? So the only condition, so for f dash of x to be equal to 0, AD minus BC would have to be equal to 0. Actually, I don't think I can do this simply in just using algebra land, so I don't think I will. I'll explain why in a second really quickly. Okay, so that means that if I sort of adjust this a little bit, AD would equal BC. Okay, AD would equal BC. Now, if I have a look at the positioning of our variables here, these two multiplied together would have to be equal to these two multiplied together. And for those people who can sort of get a sense of the AC method when we're expanding terms, expanding two binomials that are multiplied together, there might be some hints as to why that could never be a good outcome. But I'm not going to go there. I was going to go through algebraically, but off the top of my head, like, for example, I could divide through by C and do stuff like that, but I think that I might be going too far down the rabbit hole. So I will just quickly do it numerically. If you want to get ahead and try and do it out by pure algebra, please feel free to. But without using pure algebra. So right now, I'm actually taking a step back and I'm saying, if we can show why it's not a good example, not a good case in a specific example, we're then just going to say, and it would be similar for other methods. So what we're going to do is we're going to just deliberately pick some numbers that will give me AD and BC equaling each other. I could go 1, 1, 1, and 1. That's legit. A, B, C, and D can be the same number, but it doesn't feel like it's going to be very verifiable by doing it that way. So let's choose two different numbers that will multiply together, and then two other different numbers that will multiply together to the same number. I've got 4 numbers in my head. Give you a chance to think about it yourself and put them down. So what I want you to do is say, let A equal B equal C equal and D equal, so that AD equals BC. Give you a moment to do that. So 4 different numbers. Remembering, of course, they could be the same, but it does produce fairly trivial results if we make them the same. It's easier to see why it works if we choose 4 different numbers. It feels more robust in our thinking. Anyone need more time to come up with 4 numbers? Okay, I want you to follow on with me with your numbers, and I hope you've chosen different ones from me, but it doesn't matter if you have. The numbers I'm choosing are 3, and D will be 4. 3 4s are 12. And then I'm going to choose 6 and 2. 6 2s are 12. So that will give me 12 and 12 on either side. Is that okay? Who's got the same as me? That's okay. Maybe you can get ahead of me a little bit. Maybe I'll just give you the instruction. Try and get ahead of me, but then I'll unpack it straight away. But do the same thing regardless of your numbers. First things first, write down f of x is equal to, and write down your specific function, the one with the numbers that you come up with for A, B, C, and D. Not f dash, f of x. Done that? All right, next, I want you to factorize the top and factorize the bottom. They should be factorizable. So in my instance, I've got 3x plus 6 over 2x plus 4. And on the bottom, what have you got? What's your top? Okay, that's factorizable, isn't it?
That one's factorizable.
Yeah, factorize what you can. Factorize what you can. Did you get like me? Okay, we should say that in this instance, x can't equal -2, right? Because we know the denominator can't be equal to 0. So we're already saying the denominator can't be equal to 0. So it already means that x can't be equal to -2. In my instance, for you, you'll have a different value for you. Has everyone got to the same point that you've been able to factorize the top, the bottom, or both? Siggy? I've sort of just been there. Okay, cool. Everyone else with me? Okay, so when we factorize as much as we can, it turns out that the part of the expression with x's in it is the same top and bottom, right? Zoe, does that work for you? Yes or no?
Yeah.
Good. For you, Zoe? And you had the same as me. Para, what about you? Yeah. So regardless of the starting numbers we had, and it's just a very small sample set of a few here, but regardless of the starting numbers we had, the expression with the x cancels out, and we're left with the very, Rode, say it, with the very trivial function f of x equals 3 over 2, which would just be a straight line function, a horizontal line. For me, it'd be at 1.5. For you, it's at, who else had different numbers? Me. You had the same as me. You had the same as me. What did you have? Okay. 2 over 3. What did you have?
I used this change to be the same as also 3 over 2.
Okay. So we've got a few examples. It doesn't really prove it for everything, which is why I challenged the two gents down the back to do it broadly. But we can see, though, we can get a sense here that you can see that because of the way the factors would pair up, we're always going to be able to cancel out the x bit, and we're always going to be just left with a trivial function. It's a rational function, but it's not a particularly interesting one. And it certainly doesn't have a turning point, right? It's flat. It never turns. It never does anything. It's flat like that. Okay? So, therefore, for f of x to be a rational function, AC cannot equal AD cannot equal BC. Yeah? Does that make sense? AD cannot equal BC. Therefore, f dash of x does not equal 0. Do you want some fanciness? For all x. That upside down A means for all x. For all x in the real set. There's no value we can give x. So the bottom tells us there's no value we can give x to make the bottom 0, because we're automatically discounting the asymptote values. And there's no value we can give the top, the values of A, B, C, and D, because it would then just not make it a rational function. It would just be a flat line instead. So there's no turning points. Now, this comes back to the email that I sent you yesterday about the thing we were discussing before. This seems like a long way of looking at a picture and saying, I can see that it wouldn't have a turning point. It's because it's, in inverted commas, is obvious. But when we approach it algebraically, we start uncovering, this is kind of like a talk idea, really. We start uncovering some fundamental truths. It goes from being common sense, which is just like what seems to be obvious, to a fundamental axiom, right? Something which we can say must be fundamentally true by its nature. And to give you a bigger example of that, there was a famous mathematician called Bertrand Russell, and he was developing mathematical logic as a branch of mathematics. And I think this is right because I only just researched it. It took him 36 pages to prove that 1 plus 1 equals 2. Okay, 36 pages to prove that 1 plus 1 equals 2. And that's because it's not the result that's the critical thing, but it's the underlying thinking which leads us to that fact. We've gone from an assumption, 1 plus 1 equals 2, a mathematical assumption, to a fundamental underlying truth. And it took him 36 pages to do it. Okay, luckily, proving that it has no turning points did not take 36 pages for us to do. But nevertheless, I realise it does take quite a bit of effort. Okay, so that's basically it. Does anyone have any questions? What else can we say about this function? It won't be trivial. Yep. So that's what we've proven by all this stuff. The other thing we've shown as well is that since the denominator will be always positive, it won't change regardless of the value. This is the only, sorry, I'm circling the wrong thing. I'll go back to that page here. This is a constant value, never changes. Okay, once we put in the values for A, D, and B, and C, this will just be a number on top. X can be any number at all, but because we're squaring that number, this whole denominator will always be positive. So depending on what we choose for A, D, B, and C, the function's gradient will either always be negative or always positive. It will never vary. In other words, it's always decreasing or always increasing. So that's another thing that you can sort of take away from that as well. One thing I'm not going to get you to do, although it's very doable. We might actually, what have we got? A couple of bits. I'm just going to give you a window into it. We can also use the second derivative as well, right? The second derivative could be utilized in order to work out more properties about the function. What does the second derivative give us? You can determine whether it's possibly an inflection if the second derivative is equal to 0, concave up or concave down, depending on whether it's less than or greater than 0. Now, how would you approach that, do you think? Just finding the second derivative. Did you guys do it down the back? So I think I asked you to. Okay. How would you do it? Use the quotient rule again? No. Although you could. And it almost feels instinctive that you should because there's a top and a bottom. See this function here? There's no x's in it. So for all intents and purposes, I know it looks complicated, but it's just a number. You know, when I put in values for A, D, B, and C, it could be -7, or it could be 5, or it could be pi. Doesn't matter. The point is that it's just a number, right? So we've got a number over a expression. So this is the way you do it. And feel free to get ahead of me if you can. You don't have to know this. This is just to finish off the lesson, really. F dash of x, I'll start with, is equal to, what was it? AD minus BC. AD minus BC over CX, I did it again, CX plus D all squared. I could write that as this constant number AD minus BC. It's complicated, but it's just a number, multiplied by CX plus D to the power of -2. And now I can just use basic power rules. If it helps, I wouldn't do this myself, but if it helps, I could do this. Let K equal AD minus BC. Then I'd have F dash of X equals K outside of CX plus D to the power of -2. Now I'm going to use my basic derivative power rule. F dash of X is equal to, so I know I bring the number down, so it's -2, CX plus D to the power of -3. I subtract 1 from the power. And then the chain rule says, then find the derivative of the inside, which is C. So I end up with -2, C, and then K is AD minus BC. All over CX plus D cubed. Now, the interesting thing about this is that we now have a change in sign here because it's negative. CX plus D cubed is now a cube, which means that when x is negative, the denominator is potentially negative, and when x is positive, the denominator is well, at least when x is very large, x is going to the bottom is going to be positive. And so going from a square to a cube actually changes the variability of, in this case, the differentiation at that point. So like I said, you don't need to know about that, but it's just, you can keep, that's the thing about mathematics, you can continue to go down the rabbit hole and get more and more complex kind of thinking out. All right, I've gone over time, so I'll leave it there. I'll see you next Thursday. I'll give you details about block time next week. I'll pause this video.